Here we are in another series of our fascinating lectures in physical chemistry. In this lecture, this part of Lecture 4, we're going to talk about ideal gases, re-examine them in the light of the first law of thermodynamics. We learned quite a bit about ideal gases in introductory chemistry, and here we're going to continue that on a higher level. But first, let's talk about some nomenclature. Here's some terms here that we'll be using when we talk about thermodynamics. Some of them are fairly obvious and others perhaps are not. Let's first talk about adiabatic. Adiabatic means that Q is equal to 0. So you're in an adiabatic process where you go from some initial state to some final state and no heat is transferred to or from the system, then that process is called an adiabatic process. Isothermal, as you might expect, that means that the change in temperature is 0. Isobaric, bar, a unit of pressure. Isobaric means that the change in pressure is 0. Isochoric, delta V, change in volume is 0, going from the initial to final state. Isenthalpic, delta H is equal to 0, and isentropic, we haven't talked about the second law of thermodynamics, but perhaps you remember about entropy from introductory chemistry. Isentropic means that delta S equals 0. So they all seem pretty obvious, except perhaps adiabatic and isochoric. That should be choric. Sorry, misspelled. C-H-O-R-I-C. Isochoric. All right, now with that nomenclature, let's now talk about ideal gases. Here is the ideal gas law that we introduced in introductory chemistry, which we've now relabeled equation of state. That's the name for that. There are 4 state variables here: pressure, volume, number of moles, and temperature. And if you specify 3 of the 4, the 4th is specified by the equation of state. And this tells the relationship between the variables when the system is at equilibrium. Also in introductory chemistry, we talked about the kinetic molecular theory. And there we found that the kinetic energy was 3/2 RT. Let me rewrite this as this way. Kinetic energy was 3/2 nRT. So in this case, this would be the kinetic energy per mole. That will be the intensive variable, or intensive variable. But if you have n moles, this would be the kinetic energy, which is the extensive variable kinetic energy, 3/2 nRT. What we're going to show is that, or we're going to argue, that in fact the internal energy of an ideal gas is just equal to the kinetic energy. And again, I write the the extensive version of this. Ke is 3/2 nRT. And we're also going to find that the heat capacity is, for an ideal gas, is equal to 3/2 nR, heat capacity at constant volume. And the heat capacity at constant pressure is the heat capacity at constant volume plus R. All right, so that's what we're up to. All right, first let's talk about the equation of state of an ideal gas and the kinetic molecular theory. Now, on the recall the kinetic molecular theory, what we had was a container, 3-dimensional container, and within this we had a model of gas molecules. These were incompressible spheres whose volume was equal to 0, and they were in random motion. And as these molecules would strike the sides of the container, they would transfer momentum. Even though their volume is 0 in the kinetic molecular theory, they nonetheless have mass. So as the momentum of the moving gas molecule would be transferred to the sides of the container, that would give rise to pressure. And we showed in introductory chemistry that kinetic energy is for n moles is 3/2 nRT. And what I want to argue is that this kinetic energy is in fact the internal energy in the kinetic molecular theory. In the kinetic molecular theory, the only energy that these gas molecules have is the kinetic energy. If that's the only energy, then the total internal energy of the gas molecules will just be equal to the kinetic energy. And then if we look at, how U changes with temperature at constant volume, and that's defined as the heat capacity at constant volume, this then would just be 3/2 nR. Or if you want to convert heat capacity from an extensive to an intensive variable, divide by the number of moles, CV over N, which I think Ball uses maybe CVM for molar heat capacity, and that's equal to N, that's equal to 3/2 R. All right, so I hope I convinced you that the internal energy of an ideal gas is just the kinetic energy, which is 3/2 nR, and the heat capacity of a ideal gas is just 3/2 nR, or the molar heat capacity is 3/2 R. So I hope I've convinced you that. Now let's look at the relationship between heat capacity at constant pressure and heat capacity at constant volume. And what we're going to show is that they're related just by this factor of R, or this should be NR. Okay, to show that, let's start with the definition of enthalpy. All right, definition of enthalpy would be, let me just refer to my notes here. Well, I already know that. So H is equal to U plus PV. Or let's write this in the differential form. DH is equal to DU plus dPV, and at constant pressure, this is equal to du plus pdV, constant pressure. And now we're going to, let me just reset this. Now we're going to make the assumption that we have an ideal gas, and the equation of state for an ideal gas is PV is equal to nRT. So we can substitute this as du plus P. This means that V is equal to nRT over P, so that dV is d nRT over P. So this is d nRT over P. And constant pressure, ideal gas. And let's do constant number of moles N, so that this nR can be pulled out. And also P, we have constant P, is equal to du plus P times nR over P dt. The p's cancel out, so this is just equal to du plus nR dt. Now what we're going to realize is that, remember from lecture 3, or I think it was lecture 3 or maybe lecture 2, that dH is just equal to heat capacity Cp times dt, and that du is equal to heat capacity Cv, constant volume, constant pressure, dt. Remember those two things. So that this is equal to du, we'll substitute into that, dH, there's dH, we'll substitute that. So this is just Cp dt is equal to Cv, substituting in for what du is, Cv dt, plus nR dt, or in other words, as dt's go away, Cp is equal to Cv plus nR. So this gives you the relationship between the heat capacity at constant pressure and the heat capacity at constant volume. That's just the heat capacity constant pressure is the constant volume heat capacity plus NR. The heat capacity at constant pressure is greater than the heat capacity at constant volume, and for an ideal gas that is N, number of moles in the system, plus R. So what do? We start from the definition of enthalpy that was defined that way. We made some assumptions: constant pressure, ideal gas, constant N, and we were able to derive the relationship between heat capacity at constant volume and heat capacity at constant pressure. Okay, so that should take care of this slide. So we have some understanding of ideal gases on a more fundamental thermodynamic level. All right, now what I want to try to convince you is that the internal energy of a gas depends only on an ideal gas depends only on the temperature and doesn't depend on volume. All right, let's see if we can show that. And this is the argument that Ball uses in the textbook, and it's, sort of a good argument. All right, so for a gas, we said that the internal energy, and we'll talk more about this later in the course, the internal energy is a function in general of volume and temperature. All right, if that's the case, then we can write the differential du as how U changes with volume at constant temperature times dV plus how U changes with temperature at constant volume times dt. All right, let's consider the following expansion of an ideal gas. So here we have a container. Here we have a partition, and the container is insulated so that there's no heat. So this is all insulation here. So there's no heat that could be transferred to or from the surroundings. So what this means is that Q is equal to 0 because this is insulated. So another way to say this is that the process that we're going to set up for this is an adiabatic process. All right, and over here we have some gas at some pressure, and over here we have a vacuum. All right, and this is an ideal gas in here. What we're going to do is to move this container here, or sorry, not the container, move this partition, which partitions between the gas and the vacuum, so that at the end of the process, we've essentially moved it all the way down to this end, so we just have gas here. And again, it's an insulated container, so we have no heat being transferred to or from the surroundings. All right, so let's start with the first law of thermodynamics. Differential form du is equal to dq plus dw. We said that the process is adiabatic, so that dq in this case is equal to 0. And this is a PV work that it's doing, so PV, let's try PdV. I claim that's equal to 0. Why is that? Well, the gas is expanding against a pressure of 0. It's a vacuum here. So PdV, which is what the work is equal to, the pressure is 0. So even though the volume changes, it's changing against an external pressure of 0. So that is 0. So this adiabatic expansion of an ideal gas into a vacuum, this means that du is equal to 0. There's no change in the internal energy of the gas as it expands adiabatically into a vacuum. The internal energy does not change. All right, so we know that. So we know that du is equal to 0, and we also know that du is how U changes with volume at constant temperature times the change in volume plus how U changes with temperature at constant volume times the temperature change. Now, if the sum of these two has to equal 0, then, unless the very unlikely chance that that is equal to the negative of that, this implies that this term has to equal 0. For the sum of two terms has to equal 0, this term has to equal that term. And there's no reason to suppose that one would be the negative of the other. They're independent, volume and temperature, so each term has to be equal to 0. Now, this means that dV, in this case, the volume change, is not equal to 0. Why? Well, look, you're changing the volume of the gas as you expand against it. So dV is equal to 0. This implies that the second term, so that's equal to not equal to 0, that implies that this term has to equal 0. So how U changes with volume at constant temperature has to equal 0. Now we said that this term also has to equal 0. We know that dT, or the temperature, we know that dT is equal to 0. Why is that? Well, if we go back here, all right, we said that the internal energy of an ideal gas, one more here, here we go, the internal energy of an ideal gas depends only on temperature. So if the internal energy does not change, then the temperature does not change. Okay? So that means for an ideal gas, if the internal energy does not change, therefore the temperature does not change. This implies that, well, it doesn't really imply, but it doesn't have to be. Equal to 0. All right, but this is a key finding here. Oh, what have I done? Oh, shoot. Clearly I've made a mistake. All right. All right, that term has to equal 0. So this implies that U does not depend on volume. Okay, so U does not depend on volume, just depends on temperature. So U is a function, this in fact is just a function of volume, of temperature for an ideal gas. So the internal energy of an ideal gas just depends on temperature. For real gases, we'll find in the next section of this lecture that it depends not only on temperature but also on volume. But for an ideal gas, there it is, does not depend on volume. And that's an interesting finding. So I hope it convinced you that the internal energy of an ideal gas depends only on temperature and not on volume. And that sort of makes sense from the ideal gas model, the kinetic molecular theory. Go back here. So yeah, it doesn't depend on volume. You're just moving this back and forth. The only way that these molecules of gas have any energy is their kinetic energy, which depends upon temperature. Okay, that's kind of neat. I guess we already covered that, and we covered that adiabatic expansion of vacuum, gas into a vacuum. So we showed that considering that we have the internal energy, how that depends on volume is 0. In other words, it doesn't depend on volume. All right, so that's the end of the first part of Lecture 4. Hope you had a great time listening to it.